the insertion sort. That is one step. We can use the binary ID, binary search ID. Here, let us go through the whole binary search. So, most of you know the basic ID, but here, let's use the divide and conquer approach to look at this whole problem. V.1, binary search elimination. Here, let us apply the elimination method another time. Here you can see, in this class, we apply this elimination method frequently. Many questions, we need to use this simple ID. All right. Problem 11, search an ordered array. Given an ordered array, the order by default we assume ascending order, not descending order. Ordered will be ascending order. Yeah. So the array notation like this, and search key V. Question: how to find an index I such that V equals A of I? Simple question. Okay. The binary search we know very useful for real-world applications. Very useful. Okay. Yeah, very useful. All right. Here I'll give you the reference in the textbook. Let's do analysis. The idea: reduce the problem size by the ordered data property. We need to take advantage of this good property. The data is ordered, so we should take advantage of it. We should not waste it. This nice property. Okay? Yeah. All right. So the question is, how do we take advantage of this nice property? All right. Elimination method. So the idea, we want to do the minimum number of comparisons to find the index I such that V equals A to Y. Minimum number of comparisons. Okay, yeah. So, related to that elimination method, every time when we do one comparison, we want to eliminate as many elements in the array as possible from the consideration. If we can do that, then we can get the best solution. That means the minimum number of comparisons for the worst case. That is our goal. Okay, all right, yeah. Yeah, so explore the order problem. Let's draw a diagram. We try to, apply the order property for our data as much as we can. All right, so this is an ordered array, ascending order. Now we consider our first comparison. In our first comparison, we have a lot of freedom, right? What is the first element in the array we want to pick for the first comparison? We have a lot of freedom. The question is, which one is the best in the sense of elimination? Maximum number of elements to be eliminated. In that sense, the best. So when you consider this question first, we have a lot of freedom. The first one, somewhere in the middle, the last one, a lot of freedom. Okay? So when we have freedom, then we need to make the best choice. All right. Yeah. So many different ways for our first comparison. All right. So let's do some analysis in our first comparison. Question: after one comparison, how many elements can be eliminated? Okay. Yeah. First, let us look at the first case. If we compare V with the last element A sub n minus 1, what would happen?
One can be eliminated, just one element.
All right, two possibilities, right? Two possibilities. One, the best case, V greater than A n minus 1, greater than, then we can make our conclusion already, right? Yep. V cannot be found in the given array. Because V greater than the largest element in the array, then we're done. That's the best case. One comparison, we can make conclusion. Best case. Another one, other cases, and we need to do much more work. Much more work. But so we need to consider these two cases. All right, so next question. Regarding the elimination, for the worst case, remember, when we solve a problem, this problem binary search, here in the question, we do not see best case, worst case, right? But I told you before, if we do not say best case, worst case, average case, usually we assume the worst case. We work on the worst case. So here we must work on the worst case. Right. For the worst case, keep in mind, here for the elimination after one comparison, what is the worst case? The worst case occurs in this part. That means we should focus on this part, not that best case, not the best case. That's right. We don't worry. We don't worry. Best case. But for other cases, after one comparison, just like Harris said, only one element can be eliminated. That is too little, right? Nobody satisfied with this example. One element eliminated after one comparison. Okay? So that means it's not a good choice. It's not a good choice. Someone may argue we may have possibility to get the best case, right? If that we can eliminate the maximum number of elements. Some people may argue in that way. Because for the best case, we eliminate the largest number of elements. Why you say it's not good? Right? Yeah. So if you look at it that way, that's not good direction in general for problem solving. Here, let me explain why it's not a good direction at all. The reason is, I remember I mentioned there is some interesting argument in problem solving called adversary argument. If any of you still remember. So there is a thinking, one special thinking method to fight against the worst case. We use adversary argument. Here, let me explain this interesting idea another time. Because if you learn this kind of interesting thinking, so it's interesting thinking. Then, in the future, when you solve a computing problem for the worst case, because this method thinking is for the worst case. So the idea is called an adversary argument. Mainly for the worst case. Worst case solution. Right? Yeah. Here, that's the one. So, what is this argument thinking? Right? Because in order to get the worst case, we imagine there is some very smart adversary. We need to fight against some very smart adversary. Okay? The adversary's goal is trying to make our life harder. That's the goal of the adversary. Make our life harder. The adversary. Not make your life easy. Okay? It's very smart, so the adversary can take the best strategy to make your life hard. So here, we have two options, the best case and the other cases. Now, in order to fight against the worst case, we ask our adversary, which one you want to give us? Every time when there is some options, we always ask our adversaries, which one you want to give us? The adversary, very smart, the adversary would pick the smart. The adversary won't pick the best case to make your life easier, right? Yeah. Make your life harder. So the adversary pick the harder one. Okay? Yeah. Then you need to do more work. Okay? Slow down your progress. That's, the job of this adversary. Very smart. Alright. Then we need to fight. When we fight against this adversary, we need to choose some strategy such that the adversary to reduce the harm caused by our adversary. Okay? Reduce the harm. Okay? The adversary will try to make us suffer, but we want to control the damage. Or we want to minimize the damage. Okay? Yeah. So here, you can see we have a lot of freedom. In general, suppose we split an given array into two parts, right? Our first comparison, we compare some element some way. Okay? Yeah. So we split the line segment into two parts. Right? Yeah. When we do the first comparison, there are two subarrays to be considered. Okay? Yeah. Then we ask our adversary, which side you want us to take for our first comparison? The adversary definitely will pick the longest line segment. Right? Yeah? Because in that way you have to do more work. Okay? So if you split line segment into two uneven subarrays, uneven sizes for the subarray, then it's easy for the adversary just pick the larger subarray. So your key would go into the larger subarray. That's the answer from our adversary. Okay? Then we have to go there to do more work. Okay? Yeah. So then here you can see the best strategy. We want to split the given array evenly. In that case, same length, right? Same sizes. Problem. The two subarrays have the same size. Then first one, second one, no difference. In this way, this is our strategy to fight against that small elements. Okay? That's this argument. Think about that. Very interesting. Okay? All right. Very simple, but we'll try to apply this idea. Okay? So when you basically when you solve a computing problem for the worst case, when you have some options to take, so you use this adversary argument to pick the worst option to go. Okay? Yeah. All right. So then it's easy. Our strategy easy. Yeah. We just want to split the array evenly. Here, there is another interesting view we can take in Murphy's law. Because we have a better case, we have a worse case, right? Yeah. So you can also understand, use this famous word, the Murphy's law, anything that can go wrong will go wrong, right? Anything that can go wrong would be the worst case, right? The worst case, that's the worst we can get, okay? That can go wrong, will go wrong. That means we need to imagine we really have that wrong case, okay? We just assume that wrong case would happen, so we need to take care of that wrong case. So based on the Murphy's law, we can also make the right choice when you have options. Okay? That worst one, the wrong one. Okay? All right. Yeah. So compare one right in the middle. Compare the element right in the middle. That's the median. Yeah. Because here in ordered array, the one in the middle, that's the median. So here we use this concept. I mentioned this median concept many times. When you have all the number of elements, if it's in the one in the middle, no argument, right? Yeah. Because only one element in the middle. Okay? Yeah. All right. But how about you have even number of elements? Even number of elements, because there are two elements are equally in the middle, right? Same position, one left, one right, but regarding the position in the middle, they are in the same status. They have the same status. Okay? So we need to consider that situation. Here we consider even number of elements. There are two elements sit in the middle. Yeah? We can consider the left one, we call it left median. The second one, we call the right median. All right. Then, what is the final median? Right? Yeah, because here, we don't want any ambiguity here. Right? We want to have a clear answer for the median. Only one element median. Okay? Yeah. So you have to have clear. The left median is the default median. If we do not say left and right, so the left median is the default. Take the left median. Okay? Because in this way, you have the certainty. Okay? You have the certainty. But there is one problem here I would like to mention. Because in the middle school, I remember many years ago, I looked at a middle school that method, it defines the median as the average of left median and the right median. Yeah, I noticed. I saw in the library, middle school math. The definition of median is the average of left median, right median. Don't use it here, okay? Here, we are in the computer science context. We cannot use it. In math, probably it's fine, right? But in computer science, we cannot use that way. The reason is simple. The average of left median, right median, it's not any element in this array. Our median must be one of the elements in the array, okay? Yeah. In our computer science, we have to have one particular element in a given array that corresponds to the median. So don't take that average, okay? Left median. All right. Next. So we have that median here. Another interesting thing I also like to mention is called the balancing principle. Balancing. The even split, you make your data distribution very balanced, right? The most balanced is data distribution. Okay? So here there is a principle, also very useful in the solving real-world computing problem. So here I call it balancing principle. What's that? Let me give you the description of this principle. Thus, regarding the data distribution, what's that? Okay. Because in the real-world applications, when we process the given data, here, let's imagine the data is given in an array. Okay, an array. All right. Because in our data processing, it's frequently we need to consider the data distribution. So when you have freedom to choose how to distribute the data, then if you have the freedom to choose, all right, yeah, always choose the most balanced way. If you choose in that way, you get the best solution. You get, this here, the best solution means the fastest solution. Okay? The most balanced data distribution will result in the best solution, the fastest solution. It's a principle, okay? It's a principle. Principle means most of the time it's correct. But there could be some exception. You need to allow there is, some small percentage rare cases. You may have exception, but in general, 90-something% is correct. That's what the principle. Okay? Not absolute. So there could be exceptions. All right. So here you can also use the balancing principle to understand why we split our array, current array, evenly in the middle at the beginning. Okay, here you can see we have three different ways to view the same thing here. Okay, binary search. All right. Yeah. In this way, our elimination method, the impact of our elimination method. Every time you can throw away 1/2 of the elements. 1/2. Okay, yeah. That's pretty good. Right? Yeah. Because our adversary won't allow us to throw away more than 1/2, right? It's impossible because our adversary is very smart, won't allow us to throw away more than 1/2. So we are satisfied with only half of the data elimination. It's the best we can get when we fight against a very small adversary. Okay? That understanding. All right, B.2, efficiency analysis of binary search. Now, for the implementation, it's very easy, right? After you understand the first step, and the first step can be treated as a general step, because every step we do the same way. So it's a general step. So we can complete the whole binary search already. Okay? So in this part, we want to look at the worst case solution. How many comparisons do we need for the worst case? Many of you actually here, you should have an idea of that. Log base 2, right? Yeah, everybody knows the number of comparisons, log base 2 of n, okay, approximately, at least approximately. Yeah, but here I like to derive this formula precisely, precise formula. This is an approximate formula. The approximation is very good. The difference is very small. The difference is very small. But still, I like to do the rigorous logic reasoning to give you an accurate formula for the worst case. Let's do it. Diagram for the binary search. Number of comparisons for the worst case. Suppose our array, we use this line segment representation. Then we do problem size reduction. Right in the middle, so after one comparison, the problem size is reduced by 1/2. Okay. Could be left half or right half. Just 1/2. All right. Then our second comparison, another half reduction, half size reduction. 1/4 left. Okay? After two comparisons, 1/4 of the original data size left, and so on. Okay? Now, we keep doing it. We have to stop somewhere, right? You cannot do it forever. Yeah. But the question is, when should we stop? After certain number of comparisons, we have to stop. But what is that exact number of comparisons? The exact number of comparisons. Okay? Yeah. Here. So let's do this chart. Yeah. After one comparison, the data size becomes n/2. Two comparisons, data size becomes n/2 squared, and so on. Here, approximate the data size. Okay? You may argue, this expression may not be accurate because n/power of 2 may not be an integer. Right? Yeah. That's right. But here, I just say approximate size. Okay? The approximation should be very close. Think about it. Because we only drop fractions. Okay? Yeah. When we get non-integer, we only drop the fractional part. So that means the approximation is really good. Okay? So we can accept it. Yeah. All right. Then, after k comparisons, the data size becomes n/2 to the power of k. That expression, the data size. Okay? With this expression, now we try to figure out the last step for the split. Last split. Where is the last split? Okay. What is that k that corresponds to the last split? We need to use inequalities. certain inequalities to find this k number. Yeah. All right. Because we need to describe the data size for the last bit. The data size. If the data size is strictly less than 1, then it can only cover one element, right? Data size is less than 1. So you can only cover at the most one element within that little line segment. Then only one element left. Why you should not do another split, right? Yeah. That's the last split. Okay? Yeah. So we try to find that place. The data size. The data size here, n over 2 to the k, strictly less than 1. Okay? But the data size of its previous split should be greater than 1, right? The data size of its previous split should be greater than 1. Then you can do at least one split. So we need another side of the inequality. So that is this inequality. N over 2 to the k is strictly less than 1, but 1 less than or equal to n to the 2 to the k minus 1. Because that's the data size after the previous split. Okay? The previous split. Okay? Yeah. So you still you can do another split. So in this way, we can control the last split number k using two inequalities, two sides, approximate from both sides, lower bound side and upper bound side. Okay? Two sides. If you only do one side, that's not enough. Okay? Not enough. But two sides, that's enough. All right. Now we need to solve inequalities. This inequalities. All right. Remove the denominators. So we have this equivalent inequality. 2 to the k minus 1 less than or equal to, and strictly less than 2 to the k. Okay? Yeah. Because we don't like to keep the denominators, right? That's quite annoying. Okay? So we like to eliminate the denominators. After that, power of 2, because we want to represent the range for k. K. In terms of n. But a k appears in the exponent part. Exponent part. Okay? So we want to isolate k. So we take log of base 2 both sides. Log of base 2 of the spin inequality. So we get k minus 1 less than or equal to log of base 2 of n less than k. So we are very close to represent the range of k. Very close to it. Yeah. But next, we want to find the k that corresponds to the worst case solution. That's not just the range of k, that should be the exact number k. Not the range. We want to find a single answer number for k. Just the one number for k. That's our goal. So we need to do more work here. Okay? Yeah. All right. Let's continue. All right. Derive the worst case formula. start with our starting point. So let us convert this inequality in this way. Just by some simple algebra manipulation, you can see it's equivalent. So k strictly greater than log of base 2 of n, but less than or equal to 1 plus log of base 2 of n. Yes. All right. Yeah. Okay. Yeah. But here, this you can see in this new inequality. One side, the inequality contains the equal sign. But the other side, the inequality does not contain the equal sign. Okay? Yeah. That's a difference. Although the difference is very small, very little, but it is a difference. Okay? When there is a difference like this, that means we may have some room to improve. We may have some room to improve it. Okay? Yeah. Because we want to find the best solution. Okay? So we need to do the best we can. How to improve? We need to improve from here, from strictly less than sign to less than equal sign, containing equal sign. That's the equal. Including equal sign. That's the equal. Okay? Yeah. Yeah. Very little, but it is an improvement. Okay? It is one improvement. All right. How to do it? So we go back to our original before we take a natural log. All right? Let's go back. Yeah. So because we try to tighten the inequality. Someplace, somewhere, a little loose. Okay? Yeah. A little loose. We want to tighten it. This inequality is not very tight. Okay? We want to tighten it a little more. All right? Yeah. Where to tighten it? Look at this. Strictly less than sign. Not containing equal. Yeah. Because this side there is no equal sign here. That means we can tighten it to touch the equal case. Touch the equal case. That means we make it better, improve a little better, right? Yep. Look at it. So here, let's focus on this part. And strictly less than 2 to the kth power. Yep. So this is correct. And strictly less. And strictly less than 2 to the kth power. How do you improve this inequality to include that equal sign? Equal sign. We want to include equal sign. A is an integer. One integer is strictly than another integer, right? Yeah. Okay? Yeah. So here, one integer is n. Another integer is 2 to the k. And we know n is strictly cannot be equal. N can never be equal to 2 to the k. Okay? Yeah. So how do we write an inequality containing the equal sign? Minus 1. Because that integer is very strictly that if you reduce it by 1, it could be equal, right? But do not reduce too much, okay? Only reduce by 1. Reduce by 1, it has a chance to be equal to n. One difference. Because the smallest difference between two distinct integers is 1. Okay? Yeah. So look at this improvement. That's little improvement. In our analysis, sometimes we need to do this kind of fine-tuned job to squeeze some juice. Think about it. Sometimes we can ignore minor terms very generously, right? But sometimes we do this very, stingy job like this. Okay? Yeah. All right, here. Now, you can see n plus 1 less than or equal to 2 to the k. Okay? After that, we have to include that equal sign. That's better. Yeah. Equal sign. Yeah. So now let's take a natural, not natural one, log base 2 both sides. So we get log base 2 parenthesis n plus 1 less than or equal to k less than or equal to 1 plus log base 2 of n. This time, this inequality, both sides containing that equal sign. Okay? So that's the best that we can get. The best we can get. Okay? All right. Then, the final step. The final step. Because k is an integer, and the log base 2 of parenthesis n plus 1, not necessarily integer. In general, it's not integer. Only in some very special cases, it's an integer. In general, not. Okay? Yeah. Also, 1 plus log base 2 of n, in general, not integer. No. So two non-integer expressions, we want to make them both integer expressions. In this situation, to make a non-integer expressions to integer expressions, we have two ways. Apply floor function or ceiling function. Two ways. Floor function, rounded down. Ceiling function, rounded up. Okay? Right hand side, rounded down. Left hand side, rounded up. Okay? Make them closer to the destination integer. Okay? So our final conclusion is here. Okay? All right. Conclusion. Two formulas. Okay? All right. The first formula, K max. K sub max. The maximum number of comparisons. The K comparison number that corresponds to the maximum number of comparisons. That's the worst case, right? Maximum number, that's for the worst case. So K max equals, if we look from the left-hand side expression, by taking the ceiling function, we get this expression. Ceiling function of log base 2 parenthesis n plus 1. First expression. Second expression, K max equals, this time we use the right-hand side expression, 1 plus the floor function of log base 2 of n. Okay? Here you can see these two formulas are quite different. Yeah. Quite different, right? How do you know this K max? Yeah. Because K max must be one same number here. How do you know K max equals both? Both, right? Yeah, both. Actually, we can prove, we can do a rigorous proof to show these two expressions are the same. Equal, are the same. We can prove. Yeah? But here, I skipped that step, proof step. Okay? Yeah. But I can let you know how to prove it. Mathematical induction. Mathematical induction. Okay? Yeah? By mathematical induction, we can prove it. It's a good exercise for you. Yeah. Yeah. But but you need to do a lot of work. Okay? It can be proved. And it is also a formula in our textbook. Our textbook, we have this formula. These two expressions are the same. Okay? Yeah. They are the same, and one of the two gives us the accurate formula for the worst case efficiency for the binary search. Not approximate, everybody knows approximate number of comparisons, right? Yeah. Now there's two of them. Everybody knows this is the approximate number of comparisons. But flow function or seeding function, the accurate expression, one of these two formulas, not many people know it. Not many people know this one. Okay? Yeah. Because I tested many times before. Yeah. I read some quizzes before I put this question. Okay? For example, I gave a quiz question like this. Here, let me ask you and see if you can give me the answer, correct answer. I asked this simple question. Given an array with 32 elements, 32, n equals 32, okay? Ordered array, okay? Ordered array with 32 elements. We want to apply the binary search on this array. How many comparisons do we need for the worst case?
6.
Yes, great. 6, not 5. But most people give me 5 because 32 corresponds to 2 to the 5th power. So easy, right? But if you know this formula, 32 plus 1, 33, log of is 2, a little more than 5, right? Round it up. Seeding function 5.00 something, round it up. Okay? So you get 6. You get 6. That means you know this formula. If any student gives me 6 answer, then he or she knows this formula. Otherwise, 90-something%. Because they know this formula, log is 2 out of 10, right? Yeah. 5, it's a perfect 5 number, right? Yeah. So now after this class, you know the trick, okay? Yeah. You know the trick for the worst case. You use the accurate formula here. Okay? Not approximation formula here. All right? Approximate formula. 5 and 6, one difference, one accurate, another approximate. All right, yeah. So here we finish the topic. So this is formula given in appendix in our textbook. So here I skipped the proof. Before I went through the proof. It took me half an hour for the proof. Okay? So if I explain, I need half an hour. Apply the mathematical induction. Here I want to save that time, so I skip that. Okay. Yeah, the best case is 1. Yeah, binary search. When you do first comparison, you hit it. That's the best case, right? The best case is 1. The worst case is here. Let's use the second formula. 1 plus flow function of log is 2 of n. Now, let me ask you another question here. Can we say the average case is the best case plus the worst case divided by 2? Here I want to check your understanding of the average case. Because we know the best case. We also know the worst case. If we just take the straightforward average directly, can we get average case efficiency? Yeah. Remember, long time ago, I mentioned when you consider an average case, you should be very careful. Okay? Yeah. Do not assume this kind of average all the time. This kind of average, usually you can do it when your data distribution is in a linear way. Okay? Like insertion sort. Yeah. The number comparisons distribute in a linear fashion. Then this way is correct. But the binary search, the data distribution is not in the linear way. Why? The data distribution is not a linear. Because when you consider the number of comparisons, how many elements you need to do one comparison? Only one, right? At the root. Yeah. Binary search, how many elements in the array that corresponds to one comparison, you hit it. Only one, right? How many elements in the array corresponds to two comparisons? After two comparisons, you hit it. You have a chance to hit it. Two. Okay, why two? Let me draw a diagram. Right? One right in the middle, that's one. First one comparison. Two, if the median of left half, two, if the median and the right half also two. Okay? So for two comparisons, you two. Okay? One comparison, one. Two comparison, two. How about three comparisons? How many elements in the array that correspond to three comparisons? Four. Because one median in the first quarter, the median second quarter, median third quarter, median fourth quarter. So four elements correspond to three comparisons. You can see 1, 2, 4. The distribution like this, not a linear way, right? Power of 2 way. If linear way, that means 1, 2, 3, 4, 5. Consecutive integers. That's the linear way, right? Every time the increase is the same. Here, the increase is different. Okay? Increase is different. If increase is different, then this kind of average won't be correct. Won't be correct. Okay? All right. So what is the correct way to calculate average case? Correct way. All right. So the answer, average case efficiency. To do the general case, average case efficiency, a little hard. Although we can do it, yeah, but the formula takes some time. Takes some time, quite some time. Okay, all right. But here I want to do a simple example to show you the main idea for the average case. Calculate the average case efficiency for the binary search. But we just consider n equals 7. This 7 is a special number. 7 is a special number. So we like to take 7. Why special? Because 7 equals 2 cubed minus 1. 2 cubed minus 1. Why this number is so special? The special means when an array has this many elements, then when you draw a binary tree corresponding to the binary search comparisons, you will get a complete binary tree. Complete binary tree. You know complete binary tree, right? All the levels are full. That's the complete binary tree. Okay? All right, so we select the simplest case to do our average case efficiency number calculation. All right. B.3, average case efficiency of binary search. All right. This time, let me draw a diagram. Then we do the calculation based on this diagram. This should be quite easy. Okay? All right. So let's draw the binary tree that corresponds to the binary search comparison states. Okay? All right. Data, 7-element sorted or ordered array. So we use this line segment. 1, 2, 3, 4, 5, 6, 7, 7 elements. Then we have a key V to be searched for. All right. Assumption, V is in the array. Yes, because there is a possibility. So people may argue, V may not be in the array, right? Yeah. So here we want to make our discussion as simple as possible. So we do not consider the case that V is not in the array. Go ahead, I will check your name. Don't worry.
I'm very sorry about it.
Don't worry. All right.
It will be in the recording, right? Recording.
Recording. Recording, always. All right. Let's do the, comparison. Level by level. The first level, top level. Top level. Yeah. Usually we call it 0. Yeah. People also call it 0. Yeah. Okay. All right. Yeah. All right. Yeah. The first comparison. Element number 4 is at the root of the binary tree. The first one to be compared with V, element number 4. So this element corresponds to comparison number 1. Okay. Then 2 branches. Left subarray branch, right subarray branch. When we go to the left subarray branch, the root of the subtree, so here, node number 2. Okay. When we go to the right subtree, the root of the right subtree, node number 6. And these 2 nodes, we need 2 comparisons. If V equals one of these 2 elements, we need to do 2 comparisons. All right? Then let's move down, left and the right. Left, node 1. Right, node 3. Okay? Yeah. For the subtree below, node 6. Left, node 5. Right, node 7. And in these 4 nodes, we need 3 comparisons. Okay? That's all the information we need here. Okay? So we draw this binary tree covering all 7 cases. All 7 cases are covered here. Okay. So our last step, average case efficiency computation. Right. We are ready to write a final formula for the average case efficiency. Okay? Yeah. So let's write it. Average case efficiency comparison number. All right. Numerator, 1 comparison node, only 1, so 1 times 1. Okay? The first one corresponds to number of comparisons. Right? Second one corresponds to number of nodes in this level, okay? Because we organize our data level by level, okay? 3 levels here. In each level, we use the same number of comparisons, okay? So the number of nodes in this level. So 1 times 1, the second term, 2 times 2, the third term, 3 times 4. Total number of nodes, 7, denominator. Okay? Now, do some simple calculation. 17 over 7. 17 over 7. Okay? 17 over 7 less than 3. 3 is the worst case, right? Strictly less than 3, but greater than 2. Greater than 2. Between 2 and 3. Between 2 and 3. That's the average case. Okay? Then, the conclusion for the general case. Like, for the general average case. Okay? General average case. Okay? All right? Yeah. So the general, here I just give you the conclusion. Okay? General, let me use this one. Okay? Our worst case, remember, worst case we use K max, right? Maximum number of comparisons, that's for the worst case. Minus K average, KPG. Worst case minus the average case less than. Okay? So you can see, for the binary search, the average case efficiency, its accurate number, usually it's not integer. Okay? Here it's some fraction. It's not usually it's not integer. Okay? Yeah. The average case efficiency, the difference between K average and K max less than 1. So you can see the average case efficiency is very close to worst case of the binary search. The difference is less than 1. That's the binary search. Okay? Yeah. So after this discussion, now you should have pretty good understanding on the binary search. So we complete the topic of the binary search. Well done, binary search. That's all we need to know about the binary search. Okay? All right, so that's it.